Welcome to part 2 of a closer look at the shift instructions. Here we are going to work through a series of examples that will demonstrate the use of shift right and shift left instructions. We'll be using both the logical shift instructions and the arithmetic shift instructions. Here I start off with the first example. I have value 1 which is assigned to 37 and I want to multiply this by 2, and the way I'm going to do this is by using the left shift instruction with a shift count of 1. So let's start. One of the things that I want to do first is to set up the output, input and the clobber list. So we know that as a result of the shift instruction the flags are going to be clobbered, so I indicate that in the clobber list, and now I have to indicate where the input is coming from. Let's say the input comes from the EAX register, so the EAX register can be mapped to our input value, which is value 1, and let's also say that the output is after the shift is going to sit in the EAX register. So let's map the output EAX register to the variable value 1 times 2. So now since I've mapped all the input and the output values, it's time to write the instruction as such. So we know we are going to use a shift left instruction, and I'm going to use the input value in EAX, which is a 32-bit value, so I'll use the shift left L version of the instruction, L flavor of the instruction, and I need to shift this by a value of 1, so the immediate value is going to be a 1, and the the input, which is the source, is going to come from EAX. So I can either do a percentage EAX, or since I already have it mapped to value 1 here, I can simply use a percentage 1. So this should take the input value 1, shift it left by 1 place, which is effectively multiplying it by 2, and then put the output in the EAX register and map it to the variable value 1 times 2, and then I just display value 1 multiplied by 2 is value 1 times 2. So let's see if our first solution works. I'm going to build it and run it, and as you can see the output is in line with our expectation. So let's now move on to the second example here. Here in the second example I want to do an unsigned division of this variable value 2. Now the one thing I'm going to do slightly differently for this example is instead of using a register source, I'm going to use a memory, the source being coming from the memory. So let's do that here. There's the output, input and the clobber list, and as we know the clobber list has to have the flags. All shifts clobber the flags, so we put the CC there. And as I said, the input, let's try to do it differently here. So I want the input to come from memory, and the input is mapped to value 2, right? And the output, we don't need to worry about that, because when the shift right instruction runs with the memory operand, the value will be generated in place. The shift happens in place, so the result will be in value 2. So let's do the shift right instruction, since we are going to do an unsigned divide, and the L is for a 32-bit operand. The shift count is going to be $1, which is because we want to divide by 2, so we are looking at a shift count of 1, and the input is going to come from memory. So once we do this, if you notice, the old value 2 has is just assigned to value 2. So we have a display message here where it just says old value 2 divided by 2, and it displays the result. So the important thing to remember is, since the source here is in memory, the shift is going to take place and modify the value in memory, so the result will be in value 2. So let's try to build this and run, and as expected we get the value of 168. Let's move to the third example here. This example is going to do a signed multiplication. So in this case we are going to do a multiplication and it is going to be signed. So for multiplication we always think about shift left, and since it's a signed multiplication we are going to use the shift arithmetic left instruction. Although the operation of SAL and SHL are identical, I just want to demonstrate the usage of SAL in this example. So we have a value -17 in value 3, and we want to multiply that by 4. So first, as usual, we set up the output, input, and the clobber list. The clobber list has the E flags. The input will let's say it's coming from the EBX register, just to keep it different, and I map it to value 3. The output will also be in the EBX register after the shift, but we will map the output to live in this variable value 3 times 4. Now we are ready to write the actual instruction. So as I said, we are looking for shift left and shift arithmetic left, and it's a 32-bit source which is in the EBX register, and here I want to multiply by 4, so the shift count is going to be 2. So I give 2 as the shift count here, and the input is going to come from the EBX register, so which I specify with %1. So this should give us the value 3 multiplied by 4, which will be -68, and that is what we see here in the as the output of the third example. So let's move on to the fourth example. Now this one we've got to be careful because we want to do a signed division. The previous example I said you could use shift arithmetic left or shift logical left, SAL or SHL. It wouldn't have made a difference here, but here, since it's a signed division, we have to make sure we are using the SAR instruction. SHR will give us bogus results here. So we want to preserve the sign bit as we are doing the right shift. So here let's again write the input, output, and the clobber list first before we write our instruction. Output, input, and the clobber list. Our input can come from the, let's say, ECX register, and we set it up to have the value 4, which is -180, and the output will also sit in the ECX register, and we map it to value 4 div 4, right, divided by 4. So here I want to write the shift arithmetic right instruction, and I will specify a shift count of $2, right? Since we are dividing by 4, we want to do a shift count of 2, and the input is going to come from the ECX register. So now that we have all the pieces done here, let's try to build this. and run it, and negative 180 after divide by 4 is negative 45, and that's what we expect. So the last example I'm going to show you is a bit tricky. Here we are given a number and we have to multiply that number by 48, but the catch is we are not supposed to use the mul instruction. We are going to do it using shifts. 48 cannot be expressed directly as a power of 2, but you could think of a number multiplied by 48 as the same number multiplied by 64 and the same number multiplied by 16, and compute the difference between the two, and you get n times 48. Another way to look at this would be to say that n times 48 is equal to n times 32 plus n times 16. So either of these approaches would work. So what we will do is, since I'm planning on following the first example here, first solution here, I will first take the number, shift left by 6, save the temporary result, and then I take the original number and then shift left by 4. So that gives me n times 16. These two results I subtract and I save it in this variable value 5 times 48, and that should give me the result. In case you are doing the second solution, you shift left by 5, save the temporary result, shift left by 4, save the temporary result, and add the two to get n times 48. So let's try this out, and I think we could just keep the temporary results in the registers instead of saving them to any temporary variables. So the clobber list is flags. Let's look to see what our input is going to be. So I'll give two inputs, one in the ECX register, which will be our input value 5, and let's do the same thing in the EBX register also, since we have to do two shifts, right? So we put value 5 in the EBX register also. Now, and we want our final value to, let's say, to sit in the ECX register, and we will map that final value to value 5 times 48. So the first instruction we want to do is shift left. You can do an arithmetic shift if you like. It's going to be the same, SHLL, and the first time I mentioned I was going to do a left shift by 6, so I'm trying to compute n times 64 here, and I left shift by 6 and I use a %1, so I use the ECX value, shift it left, so the n times 64 is now in the ECX register at the completion of this instruction. The next instruction, I am going to do a shift left of 4, and the value is coming from the EBX register, and the result of this shift, that is n times 16, is also going to live in the EBX register. So I have the temporary results in ECX and in EBX, and all that is left for me to do is to do a sub of ECX. Actually, I want to write EBX times EBX comma ECX, right? And this will put the result in of the subtract in the ECX register, which is mapped to value 5 times 48 variable. So now if we run this test, I expect value 5 times 48, I expect 480 to show up in the output. So let's try this out, and see, I have an error. Oh, I'm just missing new lines here. Adding that. hopefully that should clean it up. Yes, and so you see that the final output is a value of 480, which matches our expectations. So I hope this video was useful in understanding the operation of the different kinds of shift instructions. Thank you.